Hello class, and thanks for tuning in today. I wanted to real quickly give you an overview on what we're going to be doing for the quarter 3 homework. I know there's been a lot of questions and some a little bit of confusion on exactly what we're doing, so I'm going to hope to help you out today and give you a real quick rundown on what we're doing. So real quickly, I know that most of you are probably familiar with how we're going to plot the Skew-T log P diagram. By now we should be pretty familiar with that. If you're not, I would recommend going back and watching some of the lectures from our online lecturer, Mr. Jeff Habe, and you'll probably see some more information on that. But in case you don't, for some reason, I think it's on there, but if it's not, we're going to go ahead and run through it real quickly. I know we've covered the Skew-T in a very broad sense, but here's the Skew-T log P diagram, of course. And your temperature skews are these blue lines right here. This is it's kind of jam-packed. It's kind of a busy diagram, but nonetheless, it's the one we're going to use for this lesson. I'll zoom in just a bit more so you can hopefully see a little bit better. Okay, so basically what we're doing is, of course, the pressure is logarithmic. It's over here on the left. The amount of pressure change with distance decreases with height. So pressures change the quickest. Near the surface. And then your skewed lines are a variety of different things, right? So you have your temperature in blue, right here. Here's your temperatures in Celsius. And they come up off the Skew-T like this and skewed to the right. Okay, so here's the 20 degree isotherm. 25 would be this line right here. Here's your 30 right here, etc. Okay, and then the dew points, of course, you're going to use to find the LCL height, you'll just ascend the saturated mixing ratio lines, the isohumes lines of constant mixing ratio. That's these purple lines right here. There's 0, there's 10 right here, and so it's 15 and 20, etc. Okay, so we're going to move on from that. And so how to plot is you'll just go right here to the data file that I've included. In the instructions will tell you which data file leads to which, is a part of which portion of the assignment. Okay, so we're going to be using the sounding from April 27th, 2014. This was a tornado that struck north of Little Rock, Arkansas. The evening of April 27, 2014 at around 7 p.m. So therefore it's 0Z April 28, 2014. Okay, so for instance, we're going to go ahead and plot. I'll just show you how to do the first few. So the temperature is roughly 21.5 degrees Celsius. You can see that. So we'll go back to our sounding here, and I'll zoom in a little bit for you. So at ground level, our first reading is 21.5 degrees Celsius. Well, here's 20. We'll ascend the 20 degree Celsius isotherm, and we can see that the first data point right here for the temperature is a little to the right of the 20. So that's therefore our 21.5 degrees Celsius surface temperature that we found looking at this right here. Okay, and the dew point is roughly 21, so we can look at that. You can see they're real close here. So right in through here is going to be the dew point. Just to the right of that is where our dew point temperature is located. Okay. Then going to the next point now, we can see that. So yeah, these are real close. The dew point, of course, is to the left of the temperature, right? The dew point can never exceed the temperature. So we'll go on up a bit. I'll take you up to 850 millibars. So the temperature there is approximately 17 degrees Celsius, 16.8. So let's go to our chart and we'll find the 17 Celsius isotherm. So a little bit past 15, right? This is 10, 15, 20 right here. So we'll go a little bit past our 15 degree isotherm. That'd be 17. Right about here, we'll go up. We'll see it intersects it right there. Is that 850? Yeah, it sure looks like it's real close. Okay, it may not quite be. Actually, yeah, this is 15. So, yeah, 17, and was it 17.5? 16.8, excuse me. 16.8. Yeah, I'm sorry guys, I'm really tired. It's been a long day. Anyway, so 16.8, so roughly 17. That's right, that's what we were looking for. Okay, so 17, go up right here. Yes, that's 850 millibars. You go across, you see we're at 850. So that's where you'd plot your point. Okay, if this data wasn't here, you'd go up 17, 10, that's 15, go 2 degrees to the right, go up, go to where that intersects 850 millibars, which would be right there. You'd plot a dot. Okay, and then you just keep on going up there, and you'd have a series of dots. And then after you'd complete your series of dots, you'd then connect all your dots, okay, to form both the temperature profile here and your moisture profile or dew point profile. Okay, like I'll give you another example here. Let me get to the right page. Let's see. Okay, here we go. All right, so we'll plot the 700 millibar temperature and dew point. Okay, so this is the temperature, since we know the temperature cannot, or the dew point cannot exceed the temperature, right? So this is the dew point column, and the one to the left is the temperature profile column. All right, so we were looking for a temperature of 7.5 degrees Celsius at 700 millibars. So what we will do is we'll go to 0 degrees. This is the 5-degree isotherm. Here's 7. We'll say 7 is about right in through here. We'll go up the isotherm parallel to it at 7.5 degrees, and we'll find where that intersects the 700 millibar line, which is right here, right in this area. So you'd put a dot right there, right? And then you'd keep on going through this list, and you'd put all of your temperatures, all of your dew point temperatures, all your dew points, and then you just connect the dots. And so our 700 millibar dew point is 5.4. So we do the same thing. 5.4, that's just ever so slightly past 5. Go right up through here to 700. And that's going to put us right there. You see, that's where the line goes through. Now the line, of course, is what you'll do, right? You'll just have a series of dots and you'll play connect the dots. Okay, so that's how you plot the SkewT log P diagram. The wind data right through here, I'm having you plot that, of course, using the Hodograph. So you don't have to compile this information. You can if you want to, right, given the assignment that I gave you. So the first question is on the thermodynamics portion, of course, is to plot the SkewT log P diagram with the coordinates provided in the image titled Q3 data. That's the process we were just reviewing here on how to use the data to plot the SkewT. Okay, I hope that helped you get back on track with that. So then the second part of question 1A, is find the lifted condensation level. You know, that's just where you plot your surface temperature and dew point, and then you'll ascend the dew point up the saturated mixing ratio line, these purple lines, to where it meets the dry adiabatic ascension from the surface temperature, right? And both the dew point and temperature need to be taken from the surface. And where those intersect, the dry adiabatic ascension from the temperature, the saturated mixing ratio ascension from the dew point, the purple line, where they intersect, that'll be your lifted condensation level, or LCL. Okay, you can go back and look in the class material if you need more information on that. Now the lifted condensation level, of course, is where you ascend the moist adiabat from the LCL, because remember, below the LCL height, the parcel is not saturated. But once you go above the LCL height, and then you're rising moist adiabatically or wet adiabatically, right? You have a saturated parcel, and so then you'll follow one of these blue lines or parallel to it. It can be in between the two blue lines, but you'll go up between it and after the LCL height to the LFC height, which is where your moist adiabat line intersects the temperature profile, right? That's very important. So go back and review a little bit if that's confusing, but I know you can do it. It won't be that difficult for you. Okay, now the equilibrium level height, using our already plotted SkewT diagram here. That's way up here. That's where the cape profile, see this right here, a buoyancy profile, which is bound by the temperature profile on the left, the atmospheric environmental temperature profile, and your parcel temperature, which is this line right here. That's where those two intersect. Okay, and then above that, the parcel is no longer buoyant. Okay, and so this is known as the equilibrium height right here, where these two lines intersect. Environmental temperature and parcel temperature right here. All right, so you're going to need the data file and your plot to come to all these other conclusions here that we're discussing now. Okay, so find the minimum or lowest in surface 10 meter relative humidity. All I want you to do there is for 1D is I'd like for you to go and find where's the minimum relative humidity on the entire SkewT once you have it plotted. And for this SkewT, of course, this is not yours, right? This is not the one you'll be doing. I'm giving you a different date to do. But the minimum on this chart would be right here, okay? Because you can see the dew point is all the way left, and the temperature is right through here. So you have your greatest spread between your temperature and your dew point temperature. Therefore, the relative humidity is the least on this sounding right here. Okay. So let's go. Actually, it may be. I didn't even think about it. It may be up here, but I should say I would like for you to find it within the buoyancy profile. Where within the buoyancy profile, the cape portion of the profile, right, the vertical depth of the cape profile, is the relative humidity the least. And in that case, it's right here. Okay, so then the maximum relative humidity. What is the typically that'll be at the surface, not always, but sometimes it'll be at the surface. And with this particular question, I think I do ask specifically for the surface. So just take that dew point and temperature at the surface and enter it into the calculator that I linked you to, which is found, hold on just one moment, I'm going to get you there, this link right here. Okay, I'd really like for you to, or one like it, doesn't matter to me, but you can find online calculators where you simply enter the dew point temperature and the temperature at a certain level, and it'll give you the relative humidity. So do that for both the sounding minimum and the surface, and we'll be in good shape. 1E, the lifted index at the traditional or conventional 500 millibar level. All right, and remember that's just the difference. Go up to 500 millibars. Right here, go over. Remember, the lifted index is just the difference between your environmental temperature, right, which is the line you plotted, and the theoretical parcel temperature, which is right through here. Okay, and you'll take the difference, right? The parcel temperature always needs to be warmer for the atmosphere to be unstable. You always want your parcel temperature to be warmer, and your environmental temperature, of course, to be cooler. And so you'll subtract off the environmental temperature from the theoretical parcel temperature, and that'll give you your lifted index. Okay, so just do that. And then going down, 1F says calculate the lifted index at the level of maximum buoyancy. Okay, so what I'm asking for here is the thickest part of the cape profile, which right in through here on this sounding is here. Okay, just below 400 millibars. So wherever the difference is greatest, and it doesn't have to be at 500 millibars, that's really important, okay? Wherever the difference between the theoretical parcel temperature and the observed atmospheric environmental temperature is the greatest, that difference, that's your LMB, or level of maximum buoyancy. Sometimes it can be down low, and sometimes it can be much higher, like in a lot of plains, severe weather events. It's found much higher, and in a lot of southeast events, it's found anywhere between 400 millibars and closer down to the surface within the lowest few hundred millibars. Okay, lowest 300 to 400 millibars. So that'll take care of that question for you. Sorry guys, I'm jumping around here a lot. I know I'm really tired this evening. Okay, so let's see. Okay, so now we're going to start the, Actually, let's finish. Okay, calculate cape 1G right through here, okay? So we've got calculate the cape for this sounding using the summed lifted index method, also known as the SLIM, okay? Summed lifted index method. So what we're going to do is we're going to go and we'll take a look at this. This is actually a technique I've been working on. It's very simple for helping you to calculate cape when given an atmospheric profile, a SkewT such as this. All right, I think we're in view. All right, so the first thing you want to do is you want to, of course, plot your profile, right? You want to have your sounding plotted. And then take a look at your cape profile. And we are going to want to we're going to want to take 10 lifted index-like measurements, okay, within our cape profile. You know, our cape profile runs from the level of free convection down here all the way up to the equilibrium level right here, okay? That's the depth of your cape profile. And we're going to want to put 10 lines in here. It doesn't really matter how you space them. Typically, I like to space them fairly even, but not always. It depends on the shape of the cape profile. What you're really trying to do here, guys, is you're trying to get find the slope or the area of the cape profile. And sometimes that means, like, see down here where I have my my measurements a little closer together than up here? That's because things are changing. See how this temperature profile line is kind of zigzagging right through here? It's a little bit irregularly shaped, whereas up then through here it's a little bit more homogeneous. It's a little bit more consistent in its shape, right? So I can space the lines a little bit more consistently apart. But down here, you start getting a little bit more irregular. It kind of broadens out here, then it narrows down again, and down here it narrows again, right? Right in through here. So that's why I have a few more measurements proportionally down here as opposed to up here. So it does kind of matter where you put them, but you should come up with a nice measurement even if you don't put them like I did and kind of concentrate on the irregular parts. Even if you were just space them out evenly, it should come out okay. But you see, like right here, you have a little jagged portion in your profile. I put one there. Also put one up here where the cape profile is the widest. That's something else that can help. And then up here where the width of the buoyancy profile is pretty homogeneous, I spaced them out pretty steadily up here. All right, and so what you're going to do then after you have your 10 measurements, 2, 3, 4, 5, 6, 7, 8, 9. Actually, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, there's 10. Is you're going to measure them. You'll need to take your lifted index at these different levels, and you'll need to observe how wide it is, right? Using the degrees in Celsius. Of course, what I do is I just get a little ruler or a piece of paper, and I mark the distance, and then I'll come down here to like where these lines are equal down here, and I'll just measure across to see how many degrees Celsius that width is. Okay, so and then I'll do the same thing here, and just measure how far across it is all the way down at all 10 levels. Then you're going to use this equation down here. Okay, this is let me broaden the screen out for you so you can see it all. Still trying to get a feel for this program here. Okay. So yeah, you're going to use this equation. The depth of the cape profile is something else you're going to have to know, okay, in meters. It needs to be in meters. And in the file that I gave you, this file right here, Q3 data, that file, the PNG file, Q3 data image, that's going to have the heights in meters. So you won't even have to really do much work to find those. But here, the top of the buoyancy profile I determined was at 13,840, which is up here. See, 13,840, it's right there. You come across, there's the equilibrium level. And the bottom of the cape profile, I determined was 2425 meters, so 2,425 meters. That's all the way down here. So 2,425 is right here. You can see there's 3020 meters, there's 1389, so it's in between there, right in through there is the LFC height. Okay, so the total depth of the cape profile is 11,415 meters. Now, what you're going to want to do is you're going to want to sum these lifted index values. So all you're doing is adding up all these that you took, all 10 levels, and you're summing them up right here. And for my 10 points, I got 46.5 was my number there. So then you just, once you have the depth of the cape profile in meters, and then the sum of your lifted index values, all you do to determine cape is put your sum of lifted index values here in the numerator, and the denominator, the depth of the cape profile in meters, this value right here. And then once you have that figured out mathematically, you just multiply it by 530,000, and that will give you a very good approximation of the cape associated with this sounding. And in this example, you see I came up with 2159 from this equation using this method, the slim method right here. The actual value computed by the computer algorithm for the sounding was 2115. So this slim method estimated cape within 98% of the integral calculus method that the computer algorithm uses. So very good way of doing this. You know, it's just a shortcut if you ever need it. This is a great way to be able to determine cape, and I just would like for you guys to understand how it works. Okay, so now we're going to move on to calculating storm relative helicity. I know I already sent you a video link for doing this process on the layer centering technique, so definitely go and check out that video if you haven't already seen it. It's a really good one, but I'll just breeze through this really quick. Yeah, so to find the layer center, as I call it, the reason why I call it the layer center is because what you're doing is you're taking a middle layer halfway between the lifted condensation level, that's cloud-based, right, and the equilibrium level. And you're going, this middle line right here is halfway between the LCL and the EL, okay? And then you're going to go 100 millibars above and below it and draw lines at both of those points. That's your layer, okay? And the layer center is, of course, the first line you drew, which is halfway between LCL and EL. All right, once you've got your layer in place, you're going to come over here to your wind profile. Or if you have it in digital, in numbers, right, if you have the vectors written out, like in this data file I gave you, then it'll be even easier. You'll have the exact numbers you need. Okay, so this is our layer. And so what I did was I assigned wind level 1. It's level with this, right, with our top of our layer, approximately. And then 2, 3, 4, 5, 6, 7, 8. It doesn't matter how many wind data points you have between the bottom and the top of the layer, just as long as you consider them all that are within the layer. Okay, and then you're going to average the speed. Okay, so average the speed of each and every one of those. 30 is the first, that's up here, number 1. Number 2 is 35 knots. You can see 35 knots, 3 long barbs and 1 short one. Okay, number 3 is 35 as well. Number 4 looks like that's 45. You see how that works? 4 long barbs and a short barb. Number 5, that's 55 knots. Remember, because you have a flag, which is 50, and a short barb, which is 5. So 55 for number 5. It's right here. Looks like number 6 went down to 50. See, it's just a flag. Number 7, 50, 8, 50, and you're done. Okay? So then what you're going to do is you're going to average all those. You're going to add them up, divide by 8. That's taking the average, 43.75 knots. Okay, this is your raw storm motion. Okay, so that's before correcting for anything. Then do the same thing for the direction. Now for the direction, you're going to have to kind of eyeball it See, this one looks number one here at 260. It's almost due west, but not quite. So I called it 260 instead of 270. The next one below it, 253. You can use a protractor if you'd like to. I've gotten pretty good at just eyeballing them, just judging them with my eyes. But you can do whatever you'd like to, as long as you get the accurate angle for each and every one of these. Remember, 270 is due west, right? So this is a wind blowing almost out of the due west. One of the techniques I like to use, and this may help you, is if you were to imagine a little arrow drawn at the tip right here. Let me go ahead and just see if I can do that for you. I've been trying to get good using this software. Just imagine a little arrow drawn at the tip of each and every one of these things, these wind barbs. That's the direction that the wind is blowing. Okay, see that? So the wind is blowing that way on all of these. Okay, so that'll probably help you understand a little bit better. So it's almost out of the due west, but 260 degrees is what I called it, because it's not quite due west. All right, so once you've averaged up all your directions, you've summed them up right here, all your points, however many you have within your layer, then you'll get your number, and then you'll divide that by the number of points you have, of course, to take an average, right? 234.12 degrees was mine. And so what you'll do then is you'll come down here, you'll take your average storm motion, speed, 43.75 knots, that's here, multiplied by your direction, 234.12. Multiply those two numbers together from here and here, you'll get 10,242.75. And your value will obviously be different because you're not using the same case. And then from there, this becomes your storm motion coefficient. Okay, you see how that works? See where we get all these numbers from? Then, after you get your storm motion coefficient, you have to determine the layer of which you want to calculate storm relative helicity. So in this example, we do 0 through 1 and 0 through 3 kilometers. The 0 through 1 is very simple. All you do is come through. Let me actually back out a notch so you can see everything on the screen, okay? All right. Well, if it'll stay. Okay, so 0 through 1 kilometer. You're starting off down here. This bottom, first you want to determine what is 1 kilometer. Well, it's this little layer right through here, because we know that this is 1389 meters. This observation says 658. So our 1,000 meter reading, 1 kilometer, has to be in between those two, right? So we're going to use this wind barb measurement, because if we go straight over, that falls in between the two. So we know that that's 1,000 meters or 1 kilometer. And again, on your data file, the heights in meters are given, and those are important. And the reason they're important is for this storm relative helicity calculation and for determining your CAPE calculation, right, using the SLIM method. Okay, so how many degrees does this wind veer or change from the surface 10 meter measurement, which is right here? Remember, surface and 10 meters are synonymous. It's really not at the surface, but it's at 10 meters. The wind is observed with the wind equipment in the National Weather Service system and most other ASOS and AWOS stations across the country. Okay, so I said this observation right here was 100 out of 115 compass degrees. So out of the east-southeast. And then I said at the top of my layer for 1 kilometer, right, top of the layer for 1 kilometer right here, I said that was 190 right here. See, out of almost due south, which would be 180, but not quite. This one right here. So 190. Okay, so 190 degrees at the top of the layer, minus 115 at the bottom from this measurement, that gives you 75 degrees of wind change. That's all you really need to know. And then what's the speed change between this 10 meter observation down here and this 1 kilometer observation up here? Well, we see that there's 4 long barbs and 1 short barb. That's 45 knots. And at the surface, there's 1 long barb. That's 10 knots. 45 minus 10 is 35. Now that we have that, we multiply 75 degrees which was our wind change, by 35. That's our change in knots. So we're multiplying the wind direction change in degrees times the number of knots change, which is 35. That gives us 26,025. Okay, 2625 for that. Then we're going to do 2625 times 12.5. This is just a coefficient that I developed through some research. All right, the number really isn't anything special other than that. And that gives us 32,812.5. Okay, this is our coefficient for our 0 through 1 kilometer SRH, this number right here. Remember, we still have our storm motion coefficient over here. We can't forget about that, okay, from when we went through and did the layer centering technique for storm motion. That gives us this, okay? And so now all we're going to do is add them up. The 32,812.5 from our 0 through 1 kilometer coefficient, and then our storm motion coefficient, and then it gives you 43,055.25. Then all you're going to do is take that number and multiply it times this coefficient that, again, I developed from research, 0.0093. And that'll give you the 0 through 1 kilometer storm relative velocity right here. When I say I developed it through research from doing like dozens and dozens and dozens of cases, probably upwards of 100 cases, to develop a coefficient averaged over 100 cases. Okay, so you're going to do the same thing for the 0 through 3 kilometer layer. All right, and that will give you a very accurate, most of the time, a very accurate estimate of storm relative velocity. There are a few exceptions, but overall, it's very efficient at calculating storm relative velocity. All right, and when you go through and determine it for the 0 through 3 kilometer layer, you know, just make sure you take your measurement accurately. Check my time there, make sure I'm not running out of time. We know that it says it right here, 3,020 meters, that's 3 kilometers, just a little over. All right, so we're going to take that wind measurement right there, this one right over my cursor, and then all the way down to the surface, and then do the same thing. Find the number of degrees in the wind change from the surface to the 3,000 meter line, speed change, and then your storm motion coefficient multiplied in there in this part once you find your 0 through 3 kilometer coefficient, which is this. Okay, so go through that, and all the numbers you need, guys, are right here. And I'm going to give you plenty of time to do this homework. Don't worry. Actually, I would like for, since we're entering our secondary severe weather season, I would like to spend some time, if we can, doing some severe weather analysis. I'm probably not going to have a quarter 4 homework assignment. That may or may not happen. And if it does happen, I promise you it won't be anything overbearing. It'll probably be more practice like this. I'll probably just give you another example to work on. Okay, so what's really important to me is that you guys get exceptional at being able to do SkewTs and Hodographs, because at some point in your career, more than likely, you're going to be able to benefit from that. And so that's really my goal and purpose here. Okay, and the last thing we're going to discuss is how to plot a Hodograph. Okay, and it's really not that difficult. So again, going back to data similar to the ones that you have that I gave you in the quarter 3 data file. Except you're not going to have this theta E stuff over here on the right. Okay, so all you do to plot a SkewT, or excuse me, a Hodograph, is you're going to start with the wind information. So here, this stands for direction in degrees. This is speed in knots. Okay, so here you have 13 knots, all right, out of 170 degrees. Well, we go to our Hodograph. Here's the degrees up here. These lines right here, okay, are going to tell you your angle degrees. So 13 knots out of 170 degrees. We see the 170 is cut off, but we know it's this line right here, because here's 180, here's a 190, so we'll just go backward, 190, 180, 170. So the 170 line runs right through here, okay, and then goes back to the origin, which is right here at the end of this pink line. Okay, So there's 170, runs right up through here like this, and at 13. So 170, go up the 170 radial to at 13 knots. Here's 10, see that right there? This radial. And then we'll go up 3 past that to 13 because we know this is 20. Here's the 20 radial right here. Okay, out of 170, which is this line that you can't really see, 13 where they intersect right there. Okay, now the next point. Some of these aren't perfect because I use some other data combined with this to make this plot. Let's go back. Hang on. Yeah. Okay, so we're going to go up and look at our 500 meters plot that we did here. So here I had to actually interpolate because you don't have a 500 meter. So I had to kind of fudge it a little bit, but I don't want to cover that. We'll go up to 1 kilometer. I think that might be the next best. No, we don't have one of those either. So I made it kind of complicated. I wanted to get some official measurements, so I kind of used some VAD wind profile data, supplemented it with. But let's go up to the upper levels and maybe I can make more sense of it for you that way. 3089 meters. See, this is the height in meters, 3089. Let's go 4534 meters. Let's use that point. 4534. There we go. So I'm going to show you how to plot that one, okay? And the rest of the data is good. I just used some other data mixed in. So some of the information between here and about right in through here was supplemented from another source. So it's going to be similar using this information, but probably not identical. Okay, so for the 4534, we can see that we have a wind direction of 233 degrees at 60 knots. So 233 at 60. 233, here's 230, here's 240. See that? 230 and 240. So a little bit past 230. And actually each one of these little lines is 1. So 1, 2, 3. Right there. It's 60 knot radial right here. See that? It goes on around like this. Here's the 50. See that bold line? 50. Okay, so it's cool. You're just plotting in polar coordinates is all you're really doing here. Okay, so 233, and at 60 knots, right there, where those intersect. There's your point. Okay, and again, that's the line for 4534. You can see that's right here. 4534, 233 at 60. And that's all you're going to do for your hodograph. And then once you've got your dots plotted, see like I did, I just have a dot here, 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 there, etc. And once you get all those dots plotted, you just connect the dots with a straight edge. And you'll get your red line, which is your actual hodograph line. Okay? Then, once you get your hodograph line, I'm going to have you plot a storm motion vector. Right down here, I say I need to actually go over this one with you, and I'll do that in just a moment. But I'll try to wrap this up quickly. Assume a storm motion vector of 244 degrees at 56 knots. Okay, so you'll do the same thing for that. You'll just plot 244 at 56. That's not this case, but for this case, I'll let you guys tell me what the storm motion vector is. Take a look at this dot right here. Okay, take a look at that for a moment. Pause it if you'd like, or just try to think it through as I talk to you about it. Okay, so to find the storm motion vector, of course, you'll be plotting this data right here, 244 at 56. But I'm not gonna show you what that plot is. I'm gonna show you what this one is to use it as an example. Okay. So right off the bat, we can see we're at what, 42 knots? Because here's our speed, right? Right down here and here. Okay. Remember, the angular degrees are on the outside, all the way around like that. So for this case, I think we're looking at, here's the 240 line. Come in, so we're right on 240, aren't we? So 240 degrees at Looks like 42 knots right there. Okay. See, I believe these are these in twos? No. 1, 2, 3, 4, 5, 6. They're in sixths. So it's going to be a little bit over 42 knots. All right. So right into, so we're probably like 40, yeah, that's probably about right. 42.5, somewhere around in there. 42.5 knots at 240 degrees. Okay. 240, roughly 42.5, somewhere around in there. All righty. So you'll be plotting this one on yours. Okay. And then the storm relative wind vectors. Right here, let's cover this next. Once you have your storm motion plotted, which is that dot, then you're going to add in, you'll want to make sure that you mark your heights on your hodograph line. This red line right here, mark the heights. Mark them in bold ink or pencil so that you can know which height they are. I tell you what, I'm going to go ahead and also I'm going to pull up the assignment, the data file, this file right here. So here I have meters. You're going to want to mark these on your hodograph. As you plot the red line, make sure that you include those numbers, these values with each point somehow, so you'll know. Otherwise, you won't be able to draw in your storm relative wind vectors. So we plotted the storm motion, right? We said it was 240 at about 42.5 knots. You could call it 42 if you wanted. That's cool. Be close enough, right? You can try to get down to that minutia if you can, but I know it's difficult sometimes. So once you have your storm motion dot plotted, and at this point we have our hodograph plotted, okay, that's all we've covered in this lesson with this so far. From that point, you're going to draw lines from the storm motion vector back to the hodograph. See how these lines are leading from the storm motion vector, the arrows back to the hodograph? Those are your storm relative winds. That's how you calculate storm relative felicity graphically. When Robert Davies Jones and Lilly developed storm relative felicity back in the late 80s, this is how they initially developed it, was to be able to determine it graphically. Okay, storm relative felicity is equal to the area bound by the storm relative wind vector at the 10 meters at the surface, this one, and your chosen level up to 3 kilometers. That's the max you can do it. You can't really, you shouldn't calculate storm relative felicity much higher than 3 kilometers. It's not really meant to. In this area bound by the hodograph between 3 kilometers and the surface storm relative wind vector, that's your 0 through 3 storm relative, 0 through 3 kilometer storm relative felicity value. This area, the area swept out by that geometric shape. Okay, so you can now see, guys, how important storm motion is to figuring out storm relative felicity. Because you can see if this black dot, the storm motion dot, were further over here, if we had, say, a storm motion of 200 out of 250 degrees at 50 knots, then your black dot would be right here, you see? And imagine then how much more area would be swept out by that geometric shape. You see that? How much larger that area would be. That would be a lot more storm relative felicity, wouldn't it? Okay, so it says, the assignment says, determine, let's see, what does it say? It says, please plot these storm relative wind vectors. 10 meter, well, all you do then is go back and you'd say, here's my storm motion dot. I'm going to go back to the first wind measurement on my hodograph line. That's 10 meters, right? Okay. This would be 500 meters, right? Remember, that's why it's important to put your meters along your hodograph, your distance. In the assignment, make sure you put these along your hodograph line, which is your red line right here, that you'll form by connecting the dots, okay, with your polar coordinate points in the hodograph as you plot them. All right, so the 0 through 3 kilometer storm relative wind vector, that's just going from the storm motion point back to the hodograph at 3 kilometers. Okay, that's all that is. And then for the upper level ones, the 6 kilometer from the storm motion point or storm motion plot dot back to the hodograph at 6 kilometers, wherever that point may be. You just connect them. See? All right, now for the storm motion, you'll take it from the storm motion point back to the origin of your hodograph. So 0, 0, right back to the origin. That's your storm motion vector right there. All right, so we will look forward now and see what else we need to do. Plot these, and the reason why I don't have 500 meters, 3,000, reason why it's not even 3,000 meters, 6,000 meters for 6 kilometers, etc., is because of this data right here. See, they're not even. So I couldn't use those exact points. Use the closest ones to those even values that I could find. Okay? So for the bulk shear, that's much easier. All you do for bulk shear is you'll go back and you'll go from the 10-meter wind plot to that level. So in other words, if we wanted to find the, what is it that I put? The 5775 meter bulk shear vector, 5775, well, you'll just take it from here to the 5775 on your hodograph line. It won't be 6 kilometers. You know, it'll be the 5775. And you'll take it from the origin, draw a straight edge up to 5775, wherever that is. Okay, draw a straight line. That'll be your bulk shear vector. In this case, it's these dash lines for me. These zigzag lines, those are my upper level storm relative wind vectors. And then the color-coded ones, those are also my mid and lower level storm relative wind vectors. Okay, here and there, etc. All right, so that's how you find the bulk shear vectors. Looks like this is my 9-kilometer bulk shear vector, the dash line I'm following here, and this is my 6-kilometer one right through here. All right, you can find the bulk shear vectors before finding the storm motion if you want. You know, it's up to you the order that you take. But the bulk shear vectors, once you have the hodograph drawn, this red line, they're very easy. All you do is draw it from the 10-meter wind observation to the point you're looking to find the respective respective bulk shear vector for. So 6 kilometers is here, 9 kilometers is here. Okay? Let's move on and see what else we need to do. See, that was assuming the storm relative wind. See, yeah, okay, so we've done this. I give you the storm motion I'd like you to use for your hodograph to find all these values. Okay, yeah, using the layer centering technique, we just went over that a little while ago. And also I linked you to another video where I give a presentation on that. Determine the critical angle, which is defined by, yes, so read your instructions here, and then we'll talk about it, okay? So this is your surface storm relative wind vector, the 10 meter, this orange line right here, taken from the storm motion back to the 10-meter wind observation right there, the first one you plot, okay? So that's the surface storm relative inflow vector, storm relative wind vector. Sometimes you'll hear it referred to as the storm relative inflow vector, SRI. That's just another term for it in weather jargon. So what we want to do is, let me make sure. Okay, critical angle. Yeah, so that's the angle between the 0 through 500 meter bulk shear vector. Right, so how would you find that? Well, you have your surface wind observation in your hodograph red line, right? So here's where the hodograph starts, that's the surface. All you'll do is the instructions say to use the angle formed by the 10-meter surface storm relative wind vector, also known as the storm relative inflow vector, and the 10 through 480 meter bulk shear vector. Okay, so it's the angle between this storm relative inflow vector, surface storm relative wind vector, right here, and the 10 meter through 480 meter, or 500 meter in our case, bulk shear vector, which is from here to here, right? Because remember, all the bulk shear vector is it's connecting the 10 meter surface wind to whatever point you want to find the bulk shear vector for. So the 1 kilometer would be from here to here. 3 kilometer would be from, I don't have them marked, as I didn't want to make the map too cluttered, this hodograph too cluttered. 3 kilometer would be from here to here, a straight line. So for 500 meters, we know this is the 500 meter point on the hodograph. That's again why you want to mark your points. 500 meter, 1 kilometer, 2 kilometer, as you go up using your data. Okay, right here. Make sure to mark these on your hodograph. It will help you. Trust me. Well, there'll be no other way you can determine these other parameters unless you do. All right, so there's the 500 meters bulk shear vector. You're going to do 480 in your case. Close enough. All right, so the angle formed by the orange line, storm relative inflow vector, and this red line, this dashed dark line overlying this red line. Remember, I did my bulk shear vectors in dashes, heavy dashes, which are these. You can see there's one here. Okay, the angle formed by the red, this line, and the orange. So this angle right through here. That's what we know is critical angle. And you'll see that on, if you click on like pivotal weather, or if you use Wonderground, or not Wonderground, but there's a couple of other point and click sounding or SharpEye. If you do that, and you'll see an observation on the panel called critical angle. And that's what that is. Okay, so determine that for your case. Of course, y'all be using this data, right? You'll do that. So that's what you're going to do to find that. Of course, okay, now bulk shear. This is one of the last things we'll talk about. I know this video has run long, and I thank you for your patience. This is really important, guys. This information is critical for knowing how to forecast storms. Got to know how to do it. You really should. I know I actually had to go back and relearn how to do some of this stuff because it's been so long. And some of it's, it involves a little work. It's not too hard, but you'll definitely do well. All right. So calculate these bulk shear values. All you're doing in this case is you'll plot your hodograph, of course, using this data, right? Your wind direction and your wind speed in meters per second. Make sure you convert to knots, guys. Be sure to convert these to knots. They were given to me in meters per second, so I didn't convert them over, but you'll just go to Google, type in convert such and such meters per second to knots, and it'll do it for you right there. So make sure you use this data for your hodograph. And let me see, there was one more thing I was wanting to... Okay, so for your bulk shear values, you cannot take the reading straight off your bulk shear and just line it up on the screen and measure accordingly along one of these straight edge lines on your hodograph on here. You cannot do that. That will not tell you the amount of bulk shear. And the same thing for the storm relative wind length, barb length. You cannot just line it up and from here to here is 40 or 25 knots. You can't do that. Okay, there's more to it. So what you're going to want to do is I ask for, what was it specifically? Hold on with me, guys. Okay, so I asked for the 10 meter, that's surface, right? 10 meter through 5775 meter, and the 10 meter through 8418 meter bulk shear values. So all you'll do is 10 through 5775, you go to your chart. 5775 is right here. You'll go on over, what's the wind speed? 35.2 meters per second. So you'll convert to knots, and then you'll subtract this value at the surface from the big one, and that'll give you your bulk shear. Easy enough. Wind at the bottom of the layer subtracted by wind at the top of the layer. So you'll subtract this little guy from the big guy right there. Okay? Make sure to convert to knots. That'll get you what you need. All right, now the assessment portion. This is cool. Calculate the energy helicity index. All that is CAPE times helicity divided by 160,000. Okay, so you'll get your quantity for CAPE times helicity, and then you'll divide that quantity by 160,000. That'll give you energy helicity index, EHI. But you'll have to determine your CAPE and helicity using everything we've talked about. Okay. Calculate the sweat. Actually, our online lecturer, Mr. Jeff Havey, actually goes into that, so it's not too bad. If you can't find the sweat in lecture, just go to Google and type it in. There's actually a sweat index calculator, And I don't mind if you use that, honestly. I'll see if I can't pull it up for you. Hold on just one sec. So I'm going to go to Google. I'm going to type in calculator. And you should get it here. Let me see. Yeah, it's this one right here. I don't know if you can see. Let me shrink my screen down. You're not going to be able to see it. Okay. Hang on just a sec. Actually, no. Need to go the other way, make it bigger. All right. So, yeah, it's this one. Weather and aviation page. Severe weather threat index calculator. Okay. All you'll do is you'll enter the 850 dew point. Just go down, enter these. This S value right here, all this is you'll take the sine of the direction. You'll find the difference between the wind speed at wind direction, at 500 millibars and the wind speed, wind direction. Let me get it right. Okay, just forget I said anything. Let's start again. You'll take the difference between the wind direction at 500 millibars and the wind direction at 850 millibars. That'll give you degrees of change, right? Okay, kind of like what we were doing when we were determining storm relative felicity. So you'll find that degree difference, that angle between the wind vector at 500 and at 850. Then you'll take the sine of that number, okay? And then you'll enter, that's your S value, which will go right here, all right? And then you can see how to, the rest are self-explanatory, okay? And you'll calculate sweat. That'll give you a value. I have a little note here I wanted to share. Let me pull it up. Most typically, these are just some observations I've made. A sweat index of greater than or equal to 350 means tornadoes are possible. Greater than or equal to 450, intense tornadoes are possible. And greater than or equal to 550, violent tornadoes become possible. I've noticed a lot of times many F5 tornadoes form in environments with EHI near 600. That's not always the case, and that should not be a hard rule. But just something from years of tornado forecasting experience, especially in the southeastern United States, I've noticed that EHI, sweat values, severe weather threat index values, sweat values of around 600 correlates to F5 tornado possibility. Very loosely correlated, though. That is not a hard rule. So that's how to calculate sweat. Let's wrap this up real quick. Based on the available data, including all thermodynamic and kinematic parameters, EHI, sweat, critical angle, and overall sounding appearance, how high is the tornado threat in this situation? By the way, critical angle, typically in the southeastern United States, anything of 45, but anything between like 45 and 70 45 and 90 is going to be conducive for strong to violent tornadoes. More typically, the values run 55 through about 70, 75 will be conducive for strong to violent tornadoes. There can be exceptions if you have real strong cape that can help to accelerate the updrafts and make them stronger and stretch the updrafts, etc. That can help compensate for critical angles that are not as favorable. Typically in the plains, the critical angle values will run during big tornado days anything from 75 to 110, 115. Somewhere they're a little bit higher in the plains states. Okay, so that'll help you understand the critical angle. So you're probably in the southeast looking for a value of like 55 to 75, generally speaking, and in the plains a little bit higher. So in the overall sounding appearance, yeah, I think that's actually our last slide. So see how this case is actually from November 10th, 2002. There's a tornado outbreak in the eastern United States that went from Alabama to Ohio. There were some fatalities that day, unfortunately. It was a big day for severe weather and tornadoes. There were several F3 tornadoes, and I think even an F4 that destroyed a movie theater in Van Wert, Ohio. And this sounding was taken from Birmingham, Alabama, but supplemented with some vertical wind profile data. So basically what you're looking for is this dogleg kink right here, this little curve. See, between the surface and this 500-meter layer. And this segment is where the atmosphere is mainly dominated by speed shear. And then right here, the atmosphere becomes more dependent and contains more directional shear. See how the direction changes rapidly. Remember, these are your directions with height here. Whereas here, it's mostly speed shear, right? And then the last one we'll look at is from April 27th, 2011. This sounding came from Birmingham, Alabama. Wow, what a big day that was. I was actually living in Huntsville. That's where I'm from, Huntsville, Alabama at the time. And that was an unbelievably scary day, as many of you may know. This is the sounding from that day. Look how long the storm relative wind vectors are. Take a look at that. That is amazing. The storm motion was, I think, 52 knots at, 243 degrees, roughly 242 degrees or so. And the storms were racing. They were moving at over 60 miles an hour at times. And but one thing to notice is look at how large and curved the hodograph is. Look at how much volume is being swept out, how much area is being swept out between the, just take the 0 through 1 kilometer storm relative wind vector, which is this one. Storm motion is right here, STM. So this is our storm relative inflow vector at the surface, right? And this is our 1,000 meter storm relative wind vector. So all this area swept out right in through here. That is all 0 through 1 kilometer storm relative felicity. That is a massive area. Okay, so you can see how large the hodograph is and how it's curved. See that? This one's more straight. A lot more speed shear involved in through here. More so speed shear than directional, but this one's both. Okay, so the overall hodograph shape does play into it. And as you work more with hodographs, you'll start learning more about their character and how to read them and use intuition and understand what's going on in the atmosphere based on what you're seeing overall too. Okay, and the specifics with the vectors and the lengths and stuff. All right, guys, I sure hope this has helped. One more thing, this last question, 3D down here, based on the wind field parameters, you have to determine what do you forecast the storm mode to be. For that, I'll just leave you with this. Generally in the atmosphere, you want your bulk shear vectors and your storm relative wind vectors to be crossing the storm initiating boundary at a sharp angle. Okay, so look in this case, you have, here's my upper level storm bulk shear vectors, these dashed lines. That's how I do my bulk shear vectors. That's a 5783 meters, so almost 6 kilometers up. Bulk shear vectors almost out of the due west. Look at that, toward the due east. So east-west storm relative wind vectors as well in the zigzag lines right through here. So my bulk shear vectors, which are dashed in the upper levels, are out of the west or easterly, and also my storm relative wind vectors, my zigzag line in the upper level. That means you're going to be, the boundary is oriented almost north-south. So it'd be almost like this, right? Assuming that this is north, this is south, east, and west. Okay, so your winds are going to be blowing perpendicular to your boundary. What that does is it forces a precipitation and thermodynamic updraft easterly, not along the boundary, so the storms don't collect and collide and one updraft spill over into the next. Instead, it causes storms to be vented downstream, okay, and it prevents them from colliding into each other and forming a squall line. There's other parameters that have to be considered as well, but this east-west storm relative wind vector, zigzag, and the bulk shear vectors in dashed, that tells you something's up and it's not good. And that generally means you're going to have a lot of supercells. Okay, and if we go back and we look at this November 10th, 2002, they're not quite as east-west, but they're close. You see how long they are, and also the general direction is like east-northeast. Okay, and still that'll keep things pretty separated. Instead of forming a squall line, you'll get supercells. So consider that as you're answering this last question. And if you have any questions, let me know. I think we've covered everything pretty well. But if you do have questions, send me an email and I'll be happy to respond. Good luck on this assignment, and y'all have a great day. Bye-bye.